So we are starting this session in 1 minute. So please prepare. First speaker is okay. So the alarm rings at 10 minutes, which is 2 minutes before the end of your talk. Is it okay for you? Well,
yes.
You don't need?
Yeah.
So alarm rings at 10 minutes,
Okay.
so 2 minutes before the end of your talk.
Okay,
You have 12 minutes for talk and 3 minutes for discussion, comments.
Thank you. My name is Ashkbiz Danehkar. I am a research scientist at Numerical Scientifics. And today I will talk about the work which I did with Sally Yu and Will Gary at University of Michigan when I was postdoc fellow. And we studied the formations of Superwind and Superbubble, and we did some hydrodynamic and photoionization modelings. And this is outline of my talk. I will talk about briefly about theory behind Superwind and also how I implement hydrodynamic simulation and how I did photoionization modeling and my future plans. Here you see the image of Rosetta Nebula, which you saw this morning in invite talk by Jonathan. And there are several OB type stars, and because of thermal and kinematic feedbacks from this young massive star, we have formation of very large scale superbubble around this OB type association. And however, in some high star forming region, like Mercurian 71, which is in south of NGC 2366, there is two nodes, B and A, which high star formations, and we have a superbubble around knot B, however knot A, which has higher ionizations, and also it is very, very bright in high frequency radio image. We don't see extended bubble, and there is an indication of radiative coolings. The thermoderivative superwinds theory started by work of Chevalier-Clage in 1985. And however, this model is an adiabatic model without radiative coolings. And later, there is a semi-analytic modeling by Silich in 2004, in which he coupled the cooling function, radiative cooling function, and here we see on the right, there is a departure from adiabatic solutions because of radiative coolings. And in my work, I consider hydrodynamic simulation of radiative coolings. Here is a schematic view of different wind regions. We have 4 different wind regions, which defined by Weber in 1977. And we have 3 expanding wind regions, and we have the formation of hot bubble in temperature, also the formation of shell in density profile, and then ambient mediums. And this is the typical schematic view of wind with spherical winds. When we don't have a spherical, we have, and also because of turbulence, we have different and complicated schematic view. And here is, you see a view of how I implemented hydrodynamic simulation of time dependence, numerical modeling of thermoderivative winds. We have different input parameter, mass loading rate, terminal velocity, cluster radius, and physical condition ambient mediums. And by setting the initial and boundary conditions, I solved these hydrodynamic fluid equations, which is coupled to radiative cooling functions and photoheating functions. And I use the SED, which made by Exoplanets 99s. And to have photoheatings, I use cooling efficiency, atomic data, and so for photoheatings, I use photoionization cross sections and also SED model, which is ionizing fields, and this radiative coolings contribute to coolings, and photoheatings is contribute to photoionization. Here you see on the left you see 1D models, and on right you see there's 2D models, And if you look at the model with low velocity 250, we see a departure from adiabatic solution. Adiabatic solution is shown by dashed line, and solid line is hydrodynamics result. And in the blue lines, you see the departure from adiabatic solution because of strong radiative coolings. And based on this departure, I define different wind models, adiabatic bubble, catastrophic cooling bubble, and catastrophic cooling without bubble, AB, CB, and CC. And I defined the different wind region, and here you see the map of parameters with adiabatic bubble and catastrophic cooling with or without bubble. And we also have pressure confined winds where the formation of bubble is stirred by high pressure of ambient mediums. In this plot, you see, in this figure, you see that by increasing metallicity, we increase coolings, and also by reducing wind thermal velocity, we also increase radiative cooling effects. And here is a bigger parameter range. As you see, by increasing mass loading rate, mass loss rate, we have higher coolings. And in this figure, you see MC. MC is momentum conserving winds. Because of strong mass loading rate, we have very strong cooling, and the formation of wind and bubble totally suppressed by the strong cooling effects. And AP is pressure confined, where the propagation of bubble is stopped by high pressure of temperature of ambient medium. And I did photoionization. I used the density and temperature, which predicted by hydrodynamic simulation, and I used them as an input for cloudy models. And we have also SCD from Starbase 99. And by using those temperature and density profile, I produced emissivity profile of different line. And as you see, in top is pure photoionization, and on bottom is collision ionization combined with photoionization. And if you look at on the green line, which is oxygen 6, on the bubble, you see difference because of high temperature of bubble. We have high oxygen 6, which we don't see in pure photoionizations. And other thing is time-dependent photoionization modelings. And in the region where time scale of collision ionization is much longer of time scale of cooling, we have non-equilibrium ionizations. And by using this equation, which have recombination rate and collision ionization rate and photoionization rate, we are able to produce non-equilibrium ionization. And here we see that on the carbon 5 and 6 and oxygen 6 and 7, we have this region where time scale of collision ionization is higher than time scale of coolings. And because of this non-equilibrium ionization, we have also different between non-equilibrium ionization and collision ionization in only oxygen 6 here, and also in carbon 4 in orange on the right. And we have higher enhancement of oxygen 6 and carbon 4 because of non-equilibrium ionization and time dependence photoionization modelings. And here you see UV diagnostic diagrams. I presented this also as in poster in Focus Meeting 4. In much more detail, you can look at my poster in Focus Meeting 4. And here we see that in the region where we have higher mass load rate and high metallicity, and we have enhancement of carbon 4 on the here. And this is the region with catastrophic cooling, and we have enhancement of carbon 4. And again, in low metallicity region, in this region, we have for red, and they are also green, we have the enhancement of oxygen 6 because of radiative coolings. And by using this UV diagnostic diagram, and if we have constraint on other parameter, we may be able to find a region with catastrophic cooling. And other things is my future plans. And because we study, we have to use SED model for the Starbase region within 1 million year. And if we run Starbase 99s from 1 to, for example, 1 to 15 million year, this SED and mass loading rate will be changed. And this contribute to different effects in time-dependent photoionization modelings. So my future plan is to use time-dependent SED model made by Starbase 99 and use those mass load which predict by the model and also SED model as an input to my hydrodynamic simulation. And I will be able to produce how the emissivity evolve with time because of time-dependent and non-equilibrium photoionizations. And the other thing is because in our photoionization modeling in the hydrodynamic simulation, we simply scale the SED by distance, the power of -2. And this is not correct when we have absorptions. And in order to include absorption, we need to have detailed radiative transfer calculations. And I plan to also include radiative transfer units, which give us optical dips. And using these optical dips, we can have more accurate radiative transfer. And we also have radiative pressure, which allows us to, if we want to study radiative-driven winds, we can also implement that. And
so 1 minute.
Okay, this is summary of my talks, and I explained about the thermal derivatives, superwind theory, and adiabatic solution, which found by Charlie Kilage, and how the motivation behind radiative coolings, and I briefly explained collision ionization versus non-equal ionizations, and also I said what is my future plan for time dependence stellar physics. So if you have any question, I am happy to answer. Thank you for your attention.
Thank you very much. So let's take questions.
So thank you for this great talk. So in terms of the diagnostics, you focused on the UV lines, which are probably the best diagnostics. But of course, observationally, this is very challenging, even for HST. Are there any other diagnostics that would be useful to identify catastrophic cooling that would be easier to access than those lines?
For optical, it's difficult because in optical, we cannot diagnose, for example, BP diagram is difficult because I produce also BP diagram. But what we see that probably the oxygen 6 and carbon 4 are the best line, but we can use in combine with radio observation. If we obtain radio observation in different band, for example, from 1 centimeter to, from low frequency to high frequency, because I saw some paper, they did also radio observation. And by using a study, and because in radio, we also should separate non-thermal and thermal. By using this radio, we may be able to diagnose it better, the region with radiative cooling. But that needs also be combined with UV, but UV has some issue also.
So sorry if you said this at the beginning of the talk because I came in a little bit late, but have you looked maybe at calibrating your models against observations of clusters that are spatially resolved in the galaxy, like young clusters of massive stars?
Pardon?
Have you considered calibrating the outputs of your models against observations of star clusters in the galaxy, where you can actually resolve the stellar population and the gas dynamics as well?
Yeah, it's a very good question. We consider to compare or resolve with observation, because in this work is one publishing AppJ last year, and that non-equilibrium just accepted a few weeks ago and will be published soon. And for that, because there are few, because when in observation of UV, they are integrated over whole galaxy. So currently, we don't have much spatial resolve UV data, but the best nearby sample is, I show it in Mercurian-71, which is the closest region which high radiative coolings. After Mercurian-71 is HARO-11s. So these two examples, which is nearby object, if we have a newer, because for Mercurian-71 there is also UV plan with Hubble telescope. So using that data, we may be able to have more data on region with radiative cooling. But distance, because they integrated over whole galaxy, is much more complicated.
Yeah, okay, thank you.
Okay, other questions? It's almost time, but I have time for one quick question. Okay, please.
So I was just wondering about the last point you make here on the radiation driving. So since in one of the figures you showed that is 100,000, 1 million Kelvin plasma you're dealing with, I was just wondering.
This one?
Yeah, for example, to what degree the radiation field may help in the acceleration, since I can imagine that most of the plasmas optically tint to the radiation field perhaps, and therefore it cannot contribute significantly more to the acceleration of the outflow. So, any idea about this?
Yeah, radiating derivative wind you are talking? Radiative derivative wind?
Yeah, so you want to include radiation force in your last point, if I understood it correctly.
But the radiating will not contribute to that bubble. It will not. The radiative is about SED model of cluster. So about radiation from that, not radiation from that bubble. But that radiation from the photonization from that bubble is also right now is included in because of calculation by Cloudy. But what I planned by radiation is the radiation from the cluster at the center of in radius 0. So from that, not from bubble. Okay. In future, yes, but it became computationally expensive if we also consider radiation from that hot bubble.
I agree. Okay, thank you.
Yeah, thank you.
Okay, let's thank our speaker again.
Thank you.
So next talk is given by Varsta Ramachandran on probing the winds and the interaction of OV stars in different environments.